So hi and hello. Welcome to our channel named AlgoXploration. My name is Samir. Now in today's lecture will be the continuation of rainwater trapping problem. In the previous lecture I have shown you the two approaches of how to solve this problem. Now in this lecture I'm going to show you the third approach will be the optimized one that will be going to take the time complexity of order of n and the space complexity order of 1, that is constant. So I'll recommend you to please watch the previous lecture. Okay, now I'll give you the quick introduction of what the problem is trying to tell us. Initially they have given us an array which contains some element. Now this 3 represent the height of the building, that is 3. Okay, now if we represent this array graphically, it will look like this. Okay, this is nothing but a block which represent the height of the building. So the 0 doesn't mean that it is a space, it means that the height of the building is 0. Now the problem is asking us that we want to return how much block of water this building can hold, or let's say trap. Okay, so between these two buildings 1 unit of water can trap. For this 1 unit, for this 2 units of water it can trap, for this 1 and for this 1. So 1 1 2 1 and 1. So if we sum up all this it will be 6. So we have to return 6 as an answer. So, okay, now if we talk about this building, okay, so the height of the building is 0. First of all we have to find the maximum height of the building present on the left side. Then we have to find out the maximum height of the building present on the right side. If you talk about the left side, the maximum height is 2, and then if you talk about the right, the maximum height is 3. After finding out, we have to find the minimum of them. So minimum of left max comma right max. So here in this case the current height of the building is 0. Okay, the left max is 2 and the right max is 3. So the minimum will be 2. Okay, now from 2 we have to subtract the current height of the building, that is 0. So 2 minus 0, it will be 2. So we can see that this building is able to store 2 units of water. Okay, so in this way we are actually approaching this problem. As you can see, for every building we have to find the left max and right max, but at the end we will be needing only one answer, right? The minimum of either left max or right max, right? So what if I say that for every building we are able to find out that required height of the building, from that building we are going to subtract the current height of the building, so that idea will be the efficient one. Okay, so for this 0, 2 will be our answer, not 3. Okay, now the thing is that here in this case, in this 0 height, we found out that the height of the building that we want is present on the left side. Okay, but here we can say for this building, the left max is 3 and the right max is 2. Okay, so for this building the height of the building that we required is 2, right, which is present on the right side, right? So there is no guarantee that the height of the building that we want will be always going to present on the left side or on the right side. Okay, so we have to find it out. So due to that we will be having two variables which will be pointing on the extreme left as well as extreme right initially. Okay, so left will be pointing to the extreme left and R will be pointing to extreme right. Okay, I hope you got this. Now let's take this scenario. Now for this building, the left max is 2 and the right max is 3. Okay, now we got to know that for this building 2 will be our required answer, right? 2 will be our required answer. So 2 minus 1 will be 1. So 1 unit of water this building can hold, right? So we can say that for this building 2 will be the threshold point. Okay, again 2 will be the threshold point, not 3. Now first of all we are going to compare L and R. At every point we have to compare L and R. If it is minimum, then we will be moving that pointer. Okay, now here we can see that 0 is minimum. Okay, first of all keep the track, so 0, and then move on. Okay, now again compare L with R. Here it is a tie, so if it is a tie, here I'm actually moving the left pointer. You can move the right pointer as well. Okay, but you have to be consistent. Okay, so again if you are moving, keep the track. So till this point 1 is the highest, so I'm keeping the track of the highest building here, and then moving on. Okay, again we have to compare L and R. We can see that 0 is minimum, right? Now here in this case, since 0 is minimum, we have to compare with the left max as well. Okay, left max as well. It means that till this point, the highest height of the building is 1, and you are pointing to zeroth height of the building. So it will store some amount of water in it. And how we can calculate? Subtract 0 from the left max, right? So 1 minus 0 will be 1. It means that 1 unit of water this building can hold. After calculating, update your answer, then move on. Now, which one is minimum? Here R is minimum. Okay, if it is, then first of all update and then move on. L is pointing to 2 and R is also pointing to 2. Okay, as I said earlier, if it is a tie, if it is a tie, move the L pointer. Before moving, keep the track of the highest building till that point. Now, who is the minimum? 1 is the minimum. Okay, now see, till this point the highest height of the building is 2, and you are pointing to this building. It means that this building can store some amount of water, right? How we can find it out? We have to check, or let's say we have to compare with the left max. If you are moving, if the minimum is L, then compare with left max. If the minimum is R, then compare with right max. Okay, here in this case the minimum is L, so we have to compare with the left max. Okay, so we got to know that the left max is maximum, right? So 2 minus current height of the building, that is 1. So the answer is 1. So this building can hold 1 unit of water. Okay, after calculating, move the pointer. Again compare, is 0, or let's say L is minimum or R is minimum. Here in this case also L is minimum. Okay, then again compare, is my left max is maximum or not? Yes it is. So subtract 0 from left max. So 2 minus 0, it will be 2. Okay, so till this point, oh sorry, so for this building 2 units of water this building can hold. Okay, I forget to keep track of answer, so will be 2 then 4. Okay, so till this point 4 units of water it can hold. Let's move on. Now L is pointing to 1 and R is pointing to 2. Here also L is minimum. Okay, if it is minimum, then first of all check with the left max. Here left max is maximum, so do 2 minus 1, it will be 1. So 1 unit of water this building can hold, and then move on. Okay, now which one is minimum, 3 or 2? Here we can see that 2 is minimum. Okay, but before moving, keep the track. Okay, and then move on. After that, here also we can see that R is minimum. It is comparing with 3 and 1. So R is minimum. Now we have to check. Is my write max is maximum with R? Yes, it is. So do 2 minus 1, it will be 1. Okay. So 1 unit of water it can hold. And then move the right pointer. Again, check. Is my write max is actually greater than R? No, it's not. Then simply move. And till this point, we do not have to go further. We can stop. If my L is greater than equals to R, then we simply have to stop it. So using this approach, we can actually able to solve this problem. I'm writing the pseudocode. This might be quite overwhelming, but if you don't understand, I'll advise you to please dry run the code by yourself. Then you will get the clear idea that how the approach is actually working. So first of all, L will be 0, R will be 0, left max will be 0 initially, and right max will also be 0. Okay, so this value will all be 0. Okay, so actually the R is n minus 1. Okay, now while L is lesser than R, then we have to be in the while loop. If A of L is lesser than equals to A of R, if this is the case, then we have to first of all check if A of L is greater than left max. Okay, if this is the case, then we have to update our left max. So left max is equals to A of left. But if this is not the case, if my A of L is not greater than left max, that it means that that particular building is able to store some amount of water. So else answer plus equals to left max minus A of L. And after that, we have to do L plus plus. I hope you got this. Else, if A of L is not lesser than A of R, it means that A of R is lesser. So in this case, here also we have to check if A of R is greater than write max. If it is, then update our write max. If this is not the case, then in the else part, answer plus is equals to write max minus A of R. That's it. And after that, do R plus plus. And we are done. Simply return answer at the last. Okay, so if you talk about this pseudocode, due to the single for loop in which L and R is not actually crossing its boundary, so the time complexity will be order of n, and since we didn't take any extra space, the space complexity will be order of 1. Okay, so this approach will be quite overwhelming or quite confusing, but if you try run it by yourself, and you will get to know that how the approach is working. Okay, so that's it from my side. I'll see you in the next video. Thank you.